Сейчас должно появиться звук или звук. Okay, so the goal of first maybe half or maybe even a quarter of today's lecture is to prove Schmidt theorem, and actually started doing this last time. So we proved a couple of observations. The first is called Fitting's lemma. Fitting's lemma tells us that if we suppose that the length of some module is finite and we consider some endomorphism, so let me say just f belongs to endomorphisms as module m, then there is some positive n such that you can decompose this module into the direct sum of two. So the image, the f to the n plus the kernel, the f to the n. So, and in particular from this lemma we derive the following. So corollary, that if we assume that m is indecomposable, right, so it can be presented as sum of two submodules. So just looking at this in decomposition, one of these two things has to be 0. So from this we derived then f is important, or if this is not important, isomorphism. So there is only two options for the steps. Now, of course, I want to mention that, of course, you know these statements and perhaps even prove this Fitting's lemma in linear algebra, because if you consider a vector space as finite dimensional vector space over a field, then this is, of course, modulus of finite length. And perhaps you've seen that if you take a matrix, right, so you interpret this matrix as an endomorphism of some finite square matrix, of course, as an endomorphism of some vector space, then you might have seen this as one of the problems in the linear algebra. Okay, so what I want to show next? Well, next is another corollary, which is going to be useful when we start proving Schmidt theorem. And this is the following. Again, I assume that m is indecomposable. M is indecomposable, so I'm going to use the previous corollary. And of course, as before, length of the m is finite. And I assume that I have endomorphism f, which is in fact a sum between I running between 1 and m of some endomorphisms fi. So m is indecomposable finite length, f is this sum. So if f is an isomorphism, then there is index I such that I is an isomorphism. So essentially we can prove this by induction on this number m. So induction, of course this m is equal to 1, everything is clear. Now let's do the following. Consider a case if fm is isomorphism, then we're done. Otherwise we do the following. Of course we can, without loss of generality, assume that this f is equal to 1, because we can consider identity of the module m is the sum inverse fi. So we know that f is an isomorphism, so it makes sense to take f inverse and take the decomposition. Okay, so if this is an isomorphism, we prove this statement. Now, if this is not, we can move this from the right hand side to the left hand side and write previous identity as this identity, which is exactly the same thing. But now, since fm is not an isomorphism, this is nilpotent. And this map also has to be nilpotent. Because if this is not nilpotent, this is an isomorphism, and if this composition is isomorphism, fm has to be an isomorphism. Okay, so this is nilpotent. But now, if this is nilpotent, 1 minus something nilpotent is invertible. The inverse is given by the geometric series, part of the geometric series. So, this is nilpotent, hence this thing is isomorphism.
The previous corollary that the module is infinite.
Yes, modulus of finite length. Yes, because we derive this from the Fitting's lemma. Fitting's lemma is about modulus of finite length. So everything is about finite length. Okay, is it clear that this observation, or observe that this is, I know that fm is not an isomorphism, right? So then I want to say that this map is nilpotent. Well, for this map I have two options by this corollary. This could be isomorphism, and if this composition is isomorphism, then fm has to be an isomorphism, which is not the case. So this has to be nilpotent, and 1 minus nilpotent is always an isomorphism. So this is again an isomorphism, and we derived, we've done the step of the induction, right? So we start with an m, and now we have the same statement with some isomorphism and m minus 1. So by induction, this result follows. Okay, and last step before we prove the main theorems on lemma. Suppose I have, I think in this lemma I don't need the assumption that m is of finite length. So I just consider two maps, f and g. So f is from m to n, and g goes in the other direction, g from n to the m. And I want to assume that composition g composed with f is an isomorphism. So then the module n is isomorphic to the direct sum of two modules, the image of f plus the kernel of g. So the first step is kind of like this step here. So without loss of generality, I can assume that this composition is the identity map, the composition of the g and f, the identity. So in this case, this is the identity of m. Right. Otherwise, I just pre-compose this, or actually post-compose this. If this is an isomorphism, I just post-compose with the inverse of this map and say that this is my new map to G.
So you assume that the file length
No, I don't think that we need this. We're going to apply this lemma to the case when m and n are of finite length, but in the lemma, I don't see how I need the finite length condition. Okay, so this is clear just because you can pre-compose this with the inverse. Now, the rest of the proof is just a straightforward computation with elements. I can take x in the module n, and I can write this x as f of g of x plus x minus f of g of x, right? This is a tautological way to rewrite this, but what we achieved here is that this first summand is in the image of the map f, so this is in the image f, right? So I want to show that this holds, so I want to show two things, right? That any element is a sum of two elements, one in the image, one in the kernel, and that the intersection is trivial. So this element is in the image of f, but this is clearly in the kernel of g, because when I apply g to this thing, I'll get g of x, and then I get minus g f g, but because of this, I can cancel g and f. So what's left is just g of x. So this is in the kernel of g. So at least I know that n is the sum of these two submodules. I don't know yet that this is direct sum, but this is sum. Now let's take something in the kernel. So suppose x belongs to the image of f intersect the kernel of g. So it means that I can write this x as f of some y, because this is in the image, and at the same time I know that the g of x is equal to 0. So I'm just take the first formula and plug in this first formula into the second formula. So then I'll get that the g of f y is equal to 0. Right? So, and I know that composition of the g and f is just the identity. So this immediately tells me that y is equal to 0, but since x is f of y, x is 0. Know the proof, right? Okay, and finally, why we need all these preparations? Now this is the main theorem, and this will be the last theorem in this section about finite length modules. So the famous Schmidt theorem, Schmidt. Any module finite length can be uniquely, of course, up to isomorphism and permutations of summands. So let me say on the order summands, so can be uniquely decomposed to a direct sum of indecomposable modules. So we need to show that there is such decomposition, and we need to show uniqueness. Well, I claim that the decomposition is clear. So you take a module of finite length. If this is indecomposable, then that's the end of the whole story. If this is decomposable, you decompose this into two. The length of both summands is strictly small. Right? So if you decompose your m into m prime plus m double prime, then the length of the m prime is strictly smaller than the length of m, and the length of double prime is strictly smaller than the length of m, right? So then, if this m prime and m double prime are decomposable, that's the end. If this is not the case, you decompose m prime, you decompose m double prime, and because the length is becoming smaller and smaller, and the length is finite, you have to finish this procedure after finitely many steps. So uniqueness is more or less a trivial observation. The existence is more or less trivial observation. What's interesting in this statement is the uniqueness part. Okay, so let's prove uniqueness. So let's assume that I have two decompositions. So maybe I have decomposition, maybe I write m here. So this is one decomposition, which is the same thing as the module m. And I can decompose m into another direct sum of indecomposables. Let me call them prime. So mi prime. So in the first decomposition, maybe I have m summands. In the second decomposition, I have n summands. Let me just fix some notation. The notation that we already used when we discussed operations on modules. So you have canonical embeddings, iota s. So this is a canonical embedding of a summand into a module. And you also have canonical projection from the module to the corresponding projection, to the corresponding submodule. This is just the notation. And of course, the same is true when I put primes here. Right, so I'm going to use the same notation. So with this notation, let me consider the following maps. So Fs. So this is the composition of four maps. So this is projection of the first component in the first decomposition, so P1, then decompose this with the embedding iota S prime, compose this with the projection pi S prime, and compose this with the embedding iota 1. So this will be a map from M1 to M1. If you just look how this maps go, I hope this is clear that if you consider composition of these four maps, you get the map from M1 to M1. Now, what is the sum of all this Fs? So now S is running again between 1 and n, so this corresponds to the second decomposition. So who can tell me what the sum is? If I take the sum of all such Fs. Yeah, this will be exactly identity on the module M1. Because when you take the sum, you consider all the components here. Right? So in the sum, you just essentially just what you do, you embed this M1 into a module, and then you project back to the same component. Now, when we have this sum, we can use this corollary, which is still on the blackboard. Right? So we can claim that one of these Fs is an isomorphism. And without loss of generality, I can say that F1 is isomorphism. So without loss of generality, F1 is an isomorphism. So F1. But otherwise, if this is not F1, I just change the indexing of my decomposition. Okay, F1 is an isomorphism, and so then I use this lemma. So I want to think about this, well, F1 is a map from M1 to M1, and I want to think about this F1 as a composition of these two maps. So this composition of four maps, I think about this as composition of this map, and apply to this composition of two maps the lemma. So I can say now that by lemma, I have that M1 prime, right? So I apply this statement when S is equal to 1, so this index in the middle, S, will be equal to 1. So M1 prime is the sum of the image and the kernel of these two maps, so this will be equal to the image of the pi 1 prime composition with the iota 1, direct sum with the kernel of the pi 1 composition with the iota 1 prime by the lemma, right? But we know that M1 prime is an indecomposable module. So it means that one of these two pieces has to be a zero piece. Can we say, for example, that this image is 0? What if this is 0? Yeah, so if the image of the map is 0, then this means that the map itself is just a 0 map. And you take a composition of some 0 map and some other map, and you get an isomorphism. That's not possible. So in this decomposition, this is definitely not a 0. So it means that this kernel is a 0 submodule. But now, if you consider map pi1 prime composition with the iota 1, so this map will be a map from M1 to the M1 prime. And you can also consider, if you want, the second map, composition of the pi1 and iota 1 prime, which will be a map from M1 prime to the M1. So what we can say about these two maps? Well, if you look at the first map, well, the image is not 0, so the image and the kernel is 0, so this image of this first map is just exactly M1 prime. So this map is surjective. And this is modules of finite length. So for modules of finite length being bijective, surjective, and injective, this is three equivalent conditions, like for vector spaces. So that's an isomorphism. Now for the second map, we already know that the kernel of this map is 0, so that's an injective map, but again, because these are modules of finite length, being injective is the same thing as being bijective, so that's an isomorphism. So we actually constructed two isomorphisms. Well, probably enough, it would be enough to use just one, but both these maps give you an isomorphisms. So what we can see that in this decomposition, you can drop the first summand here and the first summand here, and by induction, you're done. So by induction, finishing the proof. Okay, and with this theorem, I'm going to finish this section about the finite length modules and go to the next section, 4.4, Artinian rings. I'm going to leave the statement of the theorem for a moment, but erase everything else. Okay, so 4.4, Artinian. So in the first proposition, I want to summarize some basic properties of Artinian rings that we're going to use later. So in this proposition, R is an Artinian ring. We have the following 5 observations. So first observation, if it's a domain, then R is a field. So in particular, every prime ideal in Artinian ring is maximal. So second property, if R is local, meaning that there is a unique maximal ideal, but by the property 1 that maximum and prime is the same thing in Artinian ring, so there's a unique prime ideal. So if R is local, then every non-unit is nilpotent. So in the local Artinian rings, elements are only units and nilpotent elements. So 3, the annihilator 0 minimal 2 is prime. 4, any ideal contains a product of ideals. So that's the property that we already know for Artinian rings from the seminar. But of course, because here I don't know, well, I'm going to show that any Artinian ring is not Artinian in fact, but when I'm doing this, I'm going to need this property. So it will be one of the steps in the proof of the main theorem. So I need to prove this separately for Artinian rings, and of course the argument will be different. And the last one, 5, so the set, maybe I just, for shortness, instead of writing the set, I just say that, because we already have this notation, spec R is finite. I can as well write spec M, right? So maximal ideals, this is the same thing. Okay, let's prove all these properties. Some of the properties are easy, some a little bit harder. So the first property is relatively easy. You take element X in the domain, Artinian domain R. You want to show that this X is invertible, or you consider the descending chain of principal ideals generated by the X to the N. So that's a descending chain, so there is a stabilization. So there is a positive N, such that ideal X to the N, or generated by the X to the N plus 1 is the same as the ideal generated by the X to the N. So in particular, we can see that there is element Y in the ring, such that I can present X to the N as something, or take element X to the N in this ideal, and consider this as something in this ideal. So it's of the form Y X to the N plus 1. Alright, but now remember that in condition 1 we assume that R is a domain. So in the domain we have this cancellation property, which is just follows because we don't have zero divisors. So I can cancel X to the N on the left and on the right. What I'll get is that 1 is YX. So Y is actually the inverse of X. So every element, well, maybe I need to say that because I don't want to consider zero element. So every non-zero element is invertible. So any domain is actually field, and in particular part follows immediately if you just take a prime ideal. Well, you take a quotient by this prime ideal. Well, you know that you get a domain, but this is in fact a field. So in fact this prime ideal was actually maximal ideal. So in particular part is immediately follows from the main observation. So that is proof of 1. Now we need to show that we have 2. Okay, so in the local ring, I assume that I take something which is not in the maximal ideal. Well, we know that in this case, this is a unit. It was one of the statements that proved in the very beginning of the course, in the maybe second or third lecture. So in the local ring, the element which is in the complement to the maximal ideal, that's a unit. But if this is not in the complement to the maximal ideal, this is in the maximal ideal, which is in this case the same thing as the Jacobson radical. And because every primes and maximals are the same, this is the same thing as the new radical. And the new radical, this is intersection of all maximal ideals, this is intersection of all prime ideals. Prime and maximal are the same, but also new radical is a set of nilpotent elements. So everything that is in maximal ideal is nilpotent, outside of the maximal ideal is a unit. 3. So we need to show that annihilator for non-zero minimal ideal is prime. Okay, so I used first part to say that Jacobson radical is the same as the new radical. This intersection in general, this is intersection of all maximal ideals, this is intersection of all prime ideals. And since being maximal and prime in Artinian ring is the same thing, this is just the same two intersections. And then I use a statement that new radical is also the same thing as all nilpotent elements in the ring. Okay, so I want to show 3. The annihilator of a non-zero minimal ideal is prime. Maybe let me just in the statement introduce notation ideal I. So the annihilator of a non-zero minimal ideal I is prime. Okay, so let me take a couple of elements that don't annihilate this ideal I. Then I need to show that the product is also doesn't annihilate. So let's say that xi is not equal to 0, yi is not equal to 0. Okay, now now I need to say that this ideal I is a minimal ideal, and definitely xi sits inside I. So this is something inside I, and this is also something inside I. By minimality, I have to conclude that these 3 ideals coincide. So this is by minimality. And then I just do the following computation. What if you look at the xy I? Well, on one hand, you can think about this as x, yi, and you know that yi is the same thing as I, so what's left is just xi, and xi is the same thing as I. So just apply these two identities in this formula, and you get that xy applied to I is the same as I. But what's important that this I is not 0. So it means if 2 elements don't annihilate this ideal, the product also doesn't annihilate the ideal. So the annihilator is prime.
What is the minimal?
Well, this is because the ring is Artinian. You can consider the set of all non-zero ideals, and you take a minimal element in this set. The set is not empty, of course, because we always have a maximal ideal, which is in this case is the same as the prime ideal. By the way, this is exactly where we use the condition that the ring is Artinian to say that there is a minimal ideal. 4. So any ideal contains a product of prime ideals. So this is probably the most interesting part of these 4 statements. So without lots of generality, yeah, but this is minimal ideal among non-zero ideals. So the set of ideals that I consider is all non-zero ideals. So in this set I can take minimal element. So without lots of generality, we may assume, so maybe we may statement for zero ideal. No, any ideal contains a zero ideal. Okay, now let S be the set of ideals which are product of prime ideals. Again, S is not empty because we always have a maximal ideal which is a prime ideal, and so that will be at least one element in this set. So suppose J not equal to 0 is a minimal element, right? So I want to derive a contradiction from this condition that J is not equal to 0. If I can start with this and obtain a contradiction, then I prove this statement, right? Because it means that in fact the minimal element is a zero ideal. So let's derive a contradiction. Now let I be a minimal element in the set ideals containing the annihilator of this ideal J. Let me just for short write the annihilator as the colon ideal. Well, clearly from the definition of the colon ideal, this is all the elements when applied to J give me 0, so that's exactly the annihilator. Annihilator of J. And I is the minimal element over this annihilator. Okay, so then I claim the following is true. If you consider ideal P, which is just the colon ideal of this annihilator, and then you take colon ideal with the ideal I. So this ideal P is prime. So why this ideal P is prime? Well, you know property 3, the annihilator of a non-zero minimal ideal is prime. This is minimal, but this is not the minimal ideal, this is minimal over this, right? What is missing is actually that this is not a 0. So, but then you just go to the quotient by this ideal and use the correspondence theorem. So this is prime by property 3 and passing to the quotient. So that's a prime ideal, and I can also write that the product of the 3 ideals P, I, and J is 0, which just follows from the definition of this ideal P. Okay, so now what we have? We have the annihilator of the ideal J. This is properly sitting inside ideal I, and ideal I, by the previous line, is sitting maybe inside, I don't know, but in the annihilator of the ideal JP. Maybe, I don't know how to write this, maybe PJ, maybe PJ is better. So this is by definition of I, and this is by the previous line. So we can say that the PJ is strictly contained inside J. That's a contradiction. Well, we know that the PJ always sits inside J. This is just because these are ideals. So this thing I want to show that they don't coincide. But if they coincide, then these two things has to coincide. But I know that there is an ideal I, which is strictly larger than this sub-ideal. So they cannot coincide. So this is the argument. And why this is contradiction? Well, because J was by construction minimal, right? So this is a product of prime ideals and also minimal. So I construct the smaller, which is definitely also a product, because if J is product, if I multiply by one more prime ideal, that's a product. So that's a contradiction with the minimality, and so the minimal element can be non-zero element. This has to be a zero element, and that's the proof of the part 4. Finally, part 5. Part 5 is actually quite simple. No, we prove that the zero ideal is a product of prime ideals. And since the zero ideal is contained in any ideal contains a product of prime ideals. Yeah. Or in particular, zero ideal you can present as some product of prime ideals. Okay, so the last part is relatively easy. So I can say that the zero ideal is the product of prime ideals, but I know that primes are the same thing as maximal ideals. Right? So this is a finite product of maximal ideals. This is contained in any maximal ideal. So M is just any maximal ideal, but we know that this means that there is I such that Mi is contained in M, and Mi is maximal. So this has to coincide. Mi is equal to M by similarity of Mi. And this is the proof of all the 5 parts of the proposition. So maybe any questions before I erase the statements and the proofs? So the hard part is actually part 4, and from part 4, 5 follows immediately. that has finite spectrum. Well, I think finite spectrum is not enough. If this is finite and discrete, then this is equivalent to being Cartesian. But in general, I think that, yeah, there are examples of the rings with finite spectrum, finite as a set, which are not Artinian. Okay, so the next theorem sometimes is called the structure theorem for Artinian rings, and it says that any Artinian ring can be uniquely, again as before, up to isomorphisms and order decomposed into a product of local Artinian rings. This product has to be finite, right? Because if the product is not finite, you get infinitely many maximal ideals. Okay. So the first observation, well, let me just fix some notation. So let me say that the set O prime or O maximal ideals, maybe I just write spec M because I already know that these are all maximal ideals. So this is the set of ideals M1, M2, Mn. So this is the list of all maximal ideals, and I know that this list has to be finite. And I also know that the zero ideal is the product of maximal ideals. So at least I know that zero is the product of M1, but perhaps I need to take this M1 several times, right? So maybe I need to write M1 to the, what notation I want, K1. And then the same for M2 and all these ideals, so Mn to the Kn. Right? So I have this. This follows immediately from the property, what, property 4, I think. Yeah. Zero ideal is a product of prime ideal. Prime is the same as maximal, so that's the product. So maybe the only subtle point here is that I don't know that these prime ideals here have power 1, so maybe I need to take ideal M1 several times, ideal M2 several times, etc. Okay, I want to say that if I take Mi to the power Ki plus Mj to the power Kj, then these two ideals are co-maximal or co-prime, which are the same things, and I can say that this is just equal to the ring. Of course, I need to assume that I is not equal to j. So can you tell me why this is true? Mi is maximal, Mj is maximal, and what? So because the Mi and Mj are maximal, you definitely can say that this is true, right? Because if you take a maximal ideal and at least something that is not in this ideal, you get the ring. But now we want to generalize this to all the powers. Well, this is a small computation with the radicals. Well, this ideal, the sum of these two ideals, is a proper ideal if and only if the radical is a proper ideal. So equivalently, for me, it would be enough to show that the radical of the Mi to the Ki plus Mj to the Kj, this is equal to the ring, right? That's the same property. But now for the radicals, we've done this little exercise, maybe from the first or second seminar, that when you consider radical the sum of two ideals, you can as well just compute the radical and of the sum of the radicals. So Mi Ki is the radical of Mj Kj. That's just the property of the radicals, but the radical of any power of any prime ideal, which is the same prime ideal, so in particular for maximal ideal. That also was one of the things that we proved on one of the first seminars. So this thing is the same as the sum of the Mi plus Mj, which we know these two ideals are co-prime, so we know that this is the ring. I don't know, maybe. So the argument is the following: this ideal is the ring itself, if and only if its radical is the ring. But for radical, we do this computation with two steps and see that this is the ring. So indeed, these two ideals, powers of maximal ideals, are co-maximal. So it means that we can obtain the Chinese remainder theorem, and the Chinese remainder theorem in this case gives the following. So we can say that map from the ring to the product of the R modulo Mi to the Ki, I is between 1 and n. So that's an isomorphism, right? Because Chinese remainder theorem in general tell us that you have the isomorphism to this product of quotients, and you also have a kernel, and the kernel is the product of these ideals, right? The product of these ideals in our case is a zero ideal. Now, all these ideals are, all these quotient rings are local Artinian. So why these are local and Artinian rings? Just a general observation: if you take ring any maximal ideal, raise this maximal ideal to some power, the quotient is the local ring. With the radicals, maybe I do this separately as an exercise. M is maximal. This quotient. Well, you also need probably the correspondence theorem. So what are maximal ideals in this quotient? These are exactly maximal ideals containing maybe prime. So maximal ideals here correspond to maximal ideals in the ring, and prime containing M to the K by the correspondence theorem. So you have this inclusion. Let's look at the radicals. We have inclusion of the ideals and inclusion of radicals, but the radical of this thing is just this maximal ideal. The radical of this maximal ideal, or clearly this maximal ideal. So by the maximality, it has to coincide. So there is only one maximal ideal M prime containing M to the k, namely just ideal M. Okay, so and I think with this observation, we proved the existence part of this theorem, right? So we only need to show the uniqueness. So suppose, as before, that you have two ways to present this as products of local Artinian rings. Now I want to say the following. So we know that the decomposition into product of rings corresponds to some idempotence. And so, and this idempotence will, if you have such decomposition, you have idempotence, which is just elements. When you have element 1 in this ring in one position, all other elements are 0. And if you have idempotent, you have a direct summand. So equivalently, you can say that you can present 1 as a two different sums of idempotence. Okay, and now we just need to do some computation with little computation with idempotence. So for example, let me take the first identity and multiply this first identity by the E1 prime. So then I'll get E1 prime is equal, so maybe I need to say that all these elements are idempotents. So then I'll get idempotent E1 prime is equal to the sum between 1 and n, E1 prime EI. So we actually proved this on the seminar, that the decomposition of the ring, say, into product of two rings corresponds to finding two non-trivial idempotents. So let's look at this identity. Well, clearly, all these elements here in the sum are still idempotent elements. Product of two idempotents, you just compute, it will be square here, and so if we look at this identity, let's take this identity and look at this identity for the ring R1 prime. So what's this idempotent in the ring R1 prime? So idempotent E1 prime. So in this ring E1 prime, this is exactly the identity element in this ring. Now here, because if you just look at these elements, we see that E1 prime EI, these are elements in the R1 prime, and these are idempotents. So we constructed a bunch of idempotents in this ring. So from this I can claim the following, that the E1 prime EI could be equal to the 0, or this could be equal to the E1 prime. There are no other options. So this is maybe the key observation. Yes, because we assume that these rings are local rings, and in the local rings there are no idempotents other than 0 and 1. So local rings are so-called connected rings. So try to prove this as an exercise, it's not hard. Natty and McDonald, I think this exercise for the first chapter. So if this is 0 and 1, and this plays the role of 1, so these are the only options. So in this sum, we have 0 elements, and maybe have elements that are equal to this element. They can be all 0, right, because this element is not 0. So we can claim that there is I such that this product is not 0, so E1 prime EI is equal to the E1 prime. So there is at least one such index I. Now, let's look at this identity as an identity inside the ring Ri. So I've done some computation in the R1 prime. Now we're moving to the another local ring Ri. Okay, so in the local ring Ri, well, that's still that's an idempotent, right, in the ring Ri, and this is non-zero idempotent. If this is non-zero idempotent, this has to be the 1 in the ring in the Ri. So the conclusion is that this is just equal to the Ei. Take this element. Well, this element, because it's product of these two elements, belongs to this local ring. That's a non-zero element, and that's an idempotent. So this has to be the 1 in the ring. 1 in the ring is this idempotent, right? So this is the same as 1 Ri. So the first idempotent in the second decomposition corresponds to equal to some idempotent in the first decomposition. So cancel these two terms and do it by induction.
It is equal to 1. So EI is
Well, because this idempotent, if you look at the ring, so this ring, this decomposition, if I write idempotence, this I can write this as well as a decomposition into, say, product of ideals. I don't know, maybe I write it like this. And these things are the same things as Ri. So an element 1 in this ring Ri, if you look at this element inside R, this is exactly this idempotent, Ei.
Product of E1 prime and EI lies in Ri.
Well, because Ri is exactly this thing, and that's an ideal. We actually, I think, use this always already here to say this is in R1 prime. Yeah. So uniqueness is the Chinese remain, the existence of the Chinese remain the theorem was something that we proved before, and the uniqueness is some just elementary computations. Well, maybe not elementary if you see this for the first time, but there's some computation with idempotent decompositions. Okay, so if you don't have any questions, I want to erase this word. We prove the structure theorem for Artinian rings. So essentially it means that when you want to study Artinian rings, it's enough to study local Artinian rings and other just products. And now the theorem that I promised when I studied Noetherian and Artinian modules, we saw that for modules being Artinian and being Noetherian are two completely separate conditions. For rings, this is not the case. We have the following Akizuki-Hopkins theorem. So the following are equivalent, So actually I'm going to write three conditions. Usually it is written as only two conditions. So R is Noetherian when dimension of the R is 0. The second condition is that the length finite, length of the ring over the same ring. Condition 3 is that R is Artinian. So this condition 2 is kind of additional condition, but it's very convenient to have this in the proof. Usually, Akizuki-Hopkins theorem is a theorem that a ring is Artinian if and only if it is Noetherian and of dimension 0. So in the proof, I'm going to go from 1 to 2, 2 to 3, 3 to 1. So let's go 1 implies 2. Now suppose by contradiction that the length of the ring is infinite, and let I be a maximal element in the set of ideals such that the length of the quotient by this ideal is infinite. So I assume that the ring is Noetherian, so I can take maximal elements in some sets. I know that this set is not empty, because, for example, I have 0 ideal here, because this is infinite, so 0 ideal is in this set. So I want to show that this ideal I is prime. So claim that I'm going to show in the moment I is prime. Okay. So if I suppose that is not prime, well, by contradiction, suppose I not prime, well, this means that I can find a couple of elements. I can find x and y such that the product is in this ideal, but x and y is not in this ideal. And I now want to look at the short exact sequence that we discussed on the seminar. The seminar that this sequence is actually a short exact sequence. Now, what we can see? We can see that I is properly contained in the I plus xr, right? X is not in the I. So this ideal I plus xr is larger. And since I is the maximal element, and this ideal is larger, this doesn't belong to the set that I consider, so I can say that the length of the quotient is finite. I was the maximal element in the set of ideals such that the quotients are infinite. So in this column ideal, so I is again strictly sitting inside this column ideal, and in this column ideal I have element y, right? So xy is an I, but y is not an I. So again, that's an ideal that is larger than ideal I. So I can conclude that the length of the R modulo the column ideal finite. And if we proved for short exact sequences that if the length of the first term and the third term are finite, then the length of the middle term is also finite. So we proved the length of the R modulo I is finite, which is a contradiction, of course. So this is a contradiction, so we know that I is a prime ideal. Okay, so what we have I is prime. So then, of course, we know that the dimension of the ring is 0. So if I is prime, then this means that I is actually maximal. This is because the dimension of the ring is 0. It means that all the maximal ideals coincide the set of all the prime ideals. So now we have what? Now we can say the following. If I look at the length of this quotient, what's the length of this quotient? No, this is not 0. This is 1. Because, well, this is a maximal submodule, so this quotient is a simple module, and the length of a simple module is 1. Right? Look at the definition of the composition series. In the composition series, the last term always 0 term. So it will be, for a simple module, it will be a composition series only one element, which is equal to the module, and the next will be a 0 module. So anyway, the length of a simple module is 1. Follows from the definition of the composition series. But that's a contradiction. 1 is a finite number, so let's contradict how we choose I. So this contradicts the condition that the length of R is infinite. So the length of R has to be finite. So we proved that 1 implies 2. How about 2 implies 3? So the length of the ring is finite. I want to say that the ring is Artinian. So 2 implies 3 is clear and automatic because finite length of a module, it means that module is Noetherian and Artinian. So in particular, let's use that the module is Artinian. This is clear. And we only need to prove the last implication, that 3 implies 1. Well, because I proved here in this claim, in this little proof, that I is prime. Now I know that the dimension of the ring is 0, and dimension of the ring is 0, this is if and only if every prime ideal is maximal. Because if the prime ideal is not maximal, you take a prime ideal and you consider maximal ideal that contains this prime ideal, and you get a length which has, well, that shows that the dimension is at least 1. So you have a chain that shows that the dimension is at least 1, not 0. By definition, the ring is Artinian if this is Artinian as a module. We defined Artinian and Noetherian rings in this way. That's not true. If you go back to the lectures, you'll see that I defined Noetherian ring which is a Noetherian as a module, Artinian ring which is Artinian as a module, and then I proved that this is equivalent to 2 other conditions. Okay, so we need to show. I start with an Artinian ring, and I want to show that this is Noetherian and dimension 0. So the fact that this is dimension 0 is clear. That is because we already know that, because of what we proved in the first proposition about Artinian rings, we already know that if you take Artinian ring, any any maximal ideal is prime. That's the same as saying that dimension is 0. So this part is clear. So we only need to show this is actually Noetherian, and we show that the length is actually finite, right? If I assume that R is Artinian, this is Noetherian if and only if the length is finite. Right, because length is finite if and only if it is Artinian and Noetherian. So Artinian is already given. I want to show this is Noetherian. It would be equivalent to show that the length is finite. So in some senses, it looks like I'm going from 3 to 2, but I just explained how actually go. In fact, I'm going from 3 to 1. Okay. So the goal is to show that the length of this ring is finite. Now next, we're going to use structure theorem. So without loss of generality, we assume that R is local, right? Because if R is not local, it is a product of local rings. If I can prove that the statement is true for each of the components, it will be true for every component. So this is local. So local maximal ideal M. So then I can say that some power of this maximal ideal is equal to 0. So that's a special case of what we already know, that the 0 is a product of prime ideals. There's only one prime ideal, so 0 is some power of this prime or maximal ideal. And I want to use this to construct a chain, finite chain of sub-ideals, which are just powers of this maximal ideal M. So if we consider this power, so that this chain, this will be a finite chain. Now let's look at the quotients. So the quotients Mi modulo Mi plus 1 are Artinian. Again, this is submodule of Artinian, quotient by another submodule, which is again Artinian, and are vector spaces over R modulo M. You can see this directly. You can take an element and you can see that there is a multiplication of this element on this quotient, or you can use the theorem that we proved, not theorem, but little observation about the tensor product, and see that this quotient isomorphic, the R modulo M tensor Mi. Right. We know how to compute such quotients with a cyclic module. If you do this, you get exactly this thing. You prove this. But if this is just any module, capital M, you know this will be a quotient of the capital M by the product of M, this ideal, and the capital M. If you just apply this for this special module, you get exactly this answer. So maybe this is the quickest way to see this as a vector space. Now we have a vector space which is Artinian, so this has to be finite dimensional. For infinite dimensional vector spaces, there is no way this could be Artinian. So then I can conclude if this is finite dimensional vector space, then the length of this thing is finite. So you get a vector space, and this vector space is Artinian. So that's a finite dimensional vector space. If in the infinite dimensional vector space, you can construct the descending. So this is a finite dimensional vector space. And if this is finite dimensional vector space, the length of finite dimensional vector space is exactly the dimension of this vector space. So the dimension is finite, the length is finite. So we have this chain. Well, this is not a composition series, but this can be kind of refined to a composition series after finitely many steps. And how many finitely many steps you need? Well, you need to take the sum of all such lengths. So this means that, or maybe you can do this kind of step by step. Remember how I proved that if the ring has finite length, this is both Artinian and Noetherian. I've done this by step. So I can take short exact sequence where embed Mn into the Mn minus 1. I have some quotient. So this is 0. So this means that quotient has finite length. So this thing has finite length, and then I continue doing the same computation, I'll see that all these things are finite length, so M will be finite length, it will be just a field, so R has to be a finite length. So well, at least this is something that we've done before. So the conclusion is if all these quotients are finite lengths, then the length of the ring R is finite. And that's the end of the proof of the Akizuki-Hopkins theorem. So I have just several minutes, and I want to spend these several minutes on examples. From the point of view of this theorem, we can think about Artinian rings in some sense as some small rings. Examples, of course, for all fields are Artinian rings. That's not a very interesting example. Well, then, for example, this quotient ring will be Artinian, which is quite clear, which is you already see this Artinian as a module. You can also generalize this, well, not really generalize, but maybe kind of analogous example would be if you take a polynomial in one variable, say you take a quotient by a principal ideal generated by one polynomial. This is again Artinian, essentially by, well, for example, I don't know, let me generalize this and maybe we discuss this together. So I take two variables, and I take a quotient by ideal, say generated by the x squared, y cubed, and say xy. Is this Artinian? Yes, that's a key observation. If you look at this ring as just a vector space over K, this is finite dimensional vector space. So let me call this R, then, well, R is not just a ring, this is K algebra, where K is a field. So the dimension of the R as a vector space is finite. And since as a vector space this is finite, this has to be Artinian because, well, in the finite dimensional vector space, it's not possible to construct the descending chain, which also will be a chain of vector subspaces. And that's a general observation. If you want kind of some class of examples of Artinian rings, well, that would be a class of examples, finite dimensional. And in fact, the converse is also true. So if the algebra Artinian dimension is finite. So the proof of this is a little bit harder, so I'm going to derive this statement later when we discuss integral extensions of rings and applications to K algebras. So it would be interesting if you can find some elementary proof, just tell me. I don't know any elementary proofs of this statement. And also I just want to mention that you can analyze example 3 using the same idea about finite dimension. So this is as a vector space is finite dimensional and the dimension is equal to the degree of this polynomial. Okay, so that's the end of today's lecture.
Thank you.